Previous class we have worked with RNNs. We have seen how do we proceed with recurrent neural networks, and also GRUs were done in the last class. So we are going to see how LSTMs work for this. Suppose you have, okay, so this was the GRU architecture that we have studied in the last class. So in this, we have seen that there is an update gate which decides how much cell state do we want to store and whether we want to forget it. So 1 minus this gate value, and this gate value decides the cell state, which is the memory of each and every GRU unit. And this decides how much activation, this cell state is same as the activation that we are passing into next cell, next unit, that is a recurrent network or recurrent cell or GRU cell. Okay, so this is the overall idea of the GRU. Now in the GRU, there is one problem that we had discussed, which was vanishing gradient and exploding gradient problem. We have seen that vanishing gradient problem is far more dangerous than even exploding gradient problem is solved by so many easier solutions, while vanishing gradient is difficult to solve. So for this, there was updation in GRUs, which was LSTM. So in LSTM, instead of using one gate, we have three gates. So there's two equations which are add-ons from GRU in LSTMs, two additional equations. So LSTMs are able to read, write, and erase. Sorry, in RNN there is a vanishing gradient problem, while in LSTM there's a vanishing gradient problem. We'll see how. So there are three gates. We will see that there is a input gate, output gate, and forget gate, which decides how much information we want to store and how much information we want to pass on to the next layer. Okay. So I hope, first of all, I hope that architecture, you should remember how do we see the architecture of a LSTM or a RNN unit. So it's something like, suppose we have some word, some sentence. Uh, Cat is uh, doing something, and uh, she is walking and doing something. Okay, this is the whole sentence. Now she is, this is dependent on cat. So that is why so this cat, this whole sentence should remember that this cat is a singular word, it's not a plural. So this means that is should not be replaced by are if it's a plural, cats if it's a cats are. So this word decides that what is the information over here. So in vanishing gradient, what happens is when we multiply these values activations reduces, and we don't give weight to this word. Now, while this problem was solved in GRUs and LSTMs, how? So this is my first layer. This is layer 1. This is layer 1. This complete is layer 1. Then we apply another, let's say LSTM layer, or sorry, RNN layer or GRU layer. I hope the architecture, you have to keep this architecture in mind, because we are because the same architecture works for all these three, RNN, GRU, and LSTM, long short-term memory networks. So in all these three, the architecture is the same, but the only thing that is different is this architecture of this cell. This is, if this is a RNN cell, it will work differently. If it's a GRU cell, it will work differently. If it's a LSTM cell, this will work differently. Now this is layer 2, and so on up to layer n. So we don't generally add layers in vertical direction. We don't add layers in vertical direction because RNN is a sequential, works for the sequential kind of data, maybe time series data, or maybe your text data. Okay, so generally we don't add more layers in vertical directions. We only keep focusing on this horizontal direction, which represents this first part represents the time step. This whole represents at time t is equals to 1. Time t is equals to 1. This is at time t is equals to 2, and so on up to t is equals to n. This is t is equals to n. Okay. So after that, after applying layer 3 over here, okay, layer 3, final layer we apply always is a dense layer, that is a softmax layer. So this is a softmax, then this is a softmax, no, this connection is not there, then this is a softmax, and you calculate the y. If you want y's in all the time steps, then you will get the y. Okay, so this is the architecture. Now so if I'm talking about there are notations like C and A. So A is the activation, A0 is coming over here, A1 is coming over here, A2 is calculating over here. Cell state, if I'm talking about C, that is cell state. So it has cell state 0, it has cell state 1, it has cell state some n at time t is equals to n. Similarly, at each and every unit, so this is one unit of a RNN cell or a GRU cell, it is having weights and biases. These weights and biases are uh, shared with all the so weights and biases with this would be same as with the second layer, third one, not layer. So in whole layer, the weights and biases are shared just as in the CNNs. In CNNs, we share weights and biases, so the process is the same. So weights and biases of layer 3 are the same. Similarly, this second layer will be having another weights and biases. So let's say it would be W2 B2. This was W3 B3. So W2 and B2 would be same over here. Now when you have seen the equations of GRU, so in GRU there are many over here if you see, so there are weights of this W, weights of C, weights of uh, R is the relevant gate. So I have told you this U last time, and this and this and this. So this R is additional. Sometimes in simple R, simple GRU, we don't add this term, but there is a variation where we add this equation. So this is basically this shows the relevance whether we want to do this updation or not, whether we want to keep this CT minus 1 or not. So this relevance is also calculated. Okay, so this shows the how relevance is the previous cell state. If previous cell state is not important, so this gate decides whether the previous cell state is important or not. Okay, so this equation is not important, and sometimes in your online, whenever you are searching, sometimes people don't use this equation, and sometimes they use this equation. So in a simple RNN, if you skip this equation, this will also be fine. So only these four equations are important, simple GRU. Now next, today we are going to see LSTM. So in LSTM, architecture will again be the same. The only thing that is different is this cell, how the working of this cell. So this cell, each and every cell is basically showing the how much calculation it is doing, how much information is storing, and how much it is passing. So in GRU, whatever it is storing, whatever it's storing as a cell state, it is passing to the same value to the next cell. So whatever is the cell state over here, it's passing as activation to the next cell state. Okay, while in RNN, it's not the case. So sorry, in LSTMs, it's not the case. So in LSTM, what happens is there are three gates. So update gate, forget gate, and output gate. In GRU, there was only one gate, that was gamma, and which decides how much value to save in the CT, and how much value to the past, how much value to store in the cell state, and how much value to pass to the next cell. Okay, while in LSTM, these three gates, that is update gate, forget gate, and output gate. So update gate is sometimes also called as input gate, output gate, and forget gate. These three gates decide how much information to be stored in a cell and how much to be passed to the next activation. Okay, so output gate decides how much to be passed to the next activation, and update and forget gate decides how much to be stored in the memory. Now the role of update and forget gates is that in GRU, if you see over here, the cell state is current cell state of a current cell is decided based on the update gate. Update gate, if update gate's value is 0, suppose if this can be, because this is a sigmoid, so range is 0 to 1. So if this value is 0, this means uh, this this term would be cancelled out, this term would cancel out, and the current cell state is exactly same as previous cell state. Okay, if you put 0 over here, so this CT is equals to CT minus 1 if gamma is equals to 0. If gamma is equals to 1, then CT is equals to this, in that case this part would cancel out and it would be C candidate T. That means if gamma is 1, cell state is updated to candidate cell state, and if it is 0, then cell state remains same whatever was the previous cell state. Okay, so there's one gate which there's one gate which decides that the previous current cell state is same as the previous cell state, or the current cell state is updated. Okay, while in LSTM there are two gates. So instead of gamma and 1 minus gamma, there is update and forget. So 1 minus gamma is again forget, and update is you want to update. So exactly same thing is happening over here, just the way of saying is different. So instead of forget gate, there was 1 minus gamma, and instead of update gate, there was gamma. Okay, so which decides whether the cell state is to be updated and whether the previous value stored or not. Now, why these two update and forget gates are used? There is a so over there, if gamma is 0, so this term would be 1, and if this term is 1, this term would be 0. While in this case, either both of these can be 0, both of these can be 1, both of these can have any value. So this means this cell state is updated depending upon how much the percentage, that is how much we want to save the previous value and how much we want to update. So this cell state is a better representation. Why? Because over here cell state is updated depending upon the how much value we want to store from the previous information and how much value we want to calculate from the current information. Okay, so this is the only difference. So there are two difference in LSTM cell with respect to GRU. First is there are two gates, update gate and forget gate, which decides how much information we want to store and how much we want to update, how much we want to keep previous value as it is and how much we want to update. So we have a choice. Okay, and second thing that is different over here is output gate. So output gate decides the how much of this cell state value comes over here, and this activation is calculated depending upon this output gate. So this output gate decides out of the whole cell state that we have calculated how much we want to pass to the next cell for the activation, for the calculation of next activation. Okay, so there are three gates, that is the only difference, rest all is the same. All these if you see weights over here, input is 80 minus 1 and xt always, so always input is the same. The only thing that is different is the number of gates in LSTM and GRU. I hope this is clear. Any questions? No questions? Okay, so this whole set of equations, these six equations, these are happening in one cell. This is cell 1. Over here all these equations are happening in cell 2, all these equations are happening in cell 3, and so on. So this is the same process that is of RNN, GRU and LSTM. Now LSTM solves the problem of vanishing gradient. How? Because in LSTM the that is at cell state that is at this cell, that is this neuron over here. So this cell state is stored, and a part of cell state is passed to the next layer. So suppose cell state was 1, and it says that cat is important while describing this whole sentence. So cell state says, okay, my memory has stored one value. This means it is giving very high weightage to this cat word, this word. Okay, and it has passed the output multiplied by cell state, some value to the activation, let's say 0.2. It has passed to the next neuron. Okay, in the next neuron it has passed, let's say, 0.2. Now over here cell state can either be kept from the previous value as it is, or it can be updated. So what happens is it can remember one this value along the sequence. It can store this one over throughout the whole sequence, and it can update activation 0.2, 0.3, 0.4 and so on. So there are two different values. So this cell state is nothing, it's just a memory. So I know that while calculating this word, I know that cat was a singular word because it has memory, something like this. And now I can calculate my activation for this. So I will say, okay, is out of is and are is giving me more activation. So is will be giving me more activation because it depends upon the cell state. So what I'm trying to say is, along, even if there is a very large sequence, very long sequence consisting of 40 words, it can store its cell state, its memory along throughout the whole sequence. It can store it can store its activation through all the words. Okay, that activation is not lost. While if you consider a simple RNN, this memory is not there. And if you multiply it, point 2 multiply by point 2 multiply by point 2, so this value is reduced to 0.2 to the power 10, which is very small. So activation reduces if you keep on multiplying while going from left to right. Okay, so this is how vanishing gradient problem is solved. It stores the memory of each and every cell, and it can store the memory throughout a very long sequence also. Okay. So this is how LSTM works better than uh, other networks. Okay. Other sequential networks. So now in unit 3 there are three sequential models that you have to study, and RNNs, GRU and LSTM. If you have any doubts about it, go through them and you can ask this to me. Okay, these three are very important. And now your unit 3 is almost done. Okay. After this we have I have discussed encoder and decoder in the previous class, so we will just have a look at that too. We will just today we are going to discuss about the applications, how we are going to use these in a text data, or in practical you will be seeing how to implement this in a time series data. Okay, so this is the architecture. This is the final diagram. This diagram you have, this is the diagram of one neuron, one cell, one neuron that is calculating all these equations. So there are always two inputs. This is at minus 1 and xt, two inputs, only two inputs, and these two decide the value of forget gate, update gate and output gate. If you see equations, so update gate, forget gate and output gate have same equations, only the w's are different, w's and b's, and w and b are the basically these are the parameters which decides what is the value of u, update gate, forget gate and output gate. Okay, so these three are calculated. Next is we have to calculate the candidate, that what is the current cell value and what is the ct minus 1 that is coming from the previous cell. ठीक है. So when to, so for this, for the calculation of this, either we will store some part of CT minus 1 and some part of candidate current calculation. So current calculation is again dependent upon whatever the previous activation and whatever the previous input. So current candidate is basically whether we want to update it or not, how much we want to update it. So this is again calculated over here using tan h. So xt is यहाँ से xt and at minus 1 is going as input and tan h is applied, so it will calculate the candidate. So this is the equation 1 over here. So equation 1 is calculated over here. Now after this we want to calculate the cell state. So cell state is dependent upon candidate and previous cell state. So over here cell state is calculated. This depends upon previous cell state CT minus 1 as well as the candidate cell state over here, which is calculated over here. So this and this is CT minus 1 and a current candidate cell state. Now how do we decide that? So update gate and forget gate decides how much we want to keep the current candidate and how much we want to keep the previous cell state. So here it's coming, this is forget gate, and forget gate is coming from here, update gate is coming from here, and if you multiply, if you add these two, this is the addition. So this is the addition over here for the equation 5. So this is the addition for the equation 5. So it will give you cell state, and this cell state is passed to the next cell, next neuron, where the calculation is to be done. So for next neuron, this becomes CT minus 1 for the next neuron. Okay. After that, we have this output gate, which decides how much we want to pass this cell state to the activation as a for calculation in the next neuron. Okay. So over here, so output gate is here and cell state we have calculated right now. So this cell state and the activation from the output gate. So you apply tan h over here, how much you want to keep this. So tan h, and if this is the multiplication, so multiplication over here, this will return the activation. Okay. So this is the final diagram of the LSTM networks. You have to by heart this because this is important. So these are the, this is, don't get confused in different equations, use the same equations, whatever same equations, whatever you are using till now. Okay. So 3 gates, candidate, cell state. One more thing, all these vectors are of same length, so whatever is the size of get gate is the same size of ith. I is the input or update gate, so same of size of all these would be the same. Okay, dimensions would be the same. Okay, so this is how one layer of LSTM looks like. There is one input, input xt minus 1 at time t minus 1 at time t plus 1. This is first neuron where calculation is happening, second neuron, third neuron, and so on. Okay. So they are explaining this in detail. We have, so what is the advantage is that write some cell content. This means that we can keep some part of previous cell and we can keep some part of current calculation. So we can keep it according to what do we want. Instead of, while in GRU, either we keep it or we discard it. So we don't have a choice that we how much we want to store it and how much we want to discard it. There was no choice. So now we have choice that how much we want to keep the current cell state and how much we want to keep the previous one. Okay. Now, how LSTM solves vanishing gradient? So we have seen that LSTM keeps a memory and re which remembers it, remembers it throughout the whole. as we have discussed that there is no guarantee that there is no vanishing gradient problem. There's no guarantee although, but yet yes, it's LSTM solve this problem somehow. Okay. Okay, LSTMs are extremely popular networks. They are used. There is a difference in GRU and LSTM. If somebody asks you that why you used GRU and why you used LSTM, so GRUs are much faster networks, and faster because it has only one gate and it has three gates. So faster and simple. GRU are simple to implement, faster, while this is a little bit slower. While if you have because we have high computational power these days, so that doesn't matter. So time doesn't matter because we are anyway able to implement these fast as well. But GRUs are generally faster than LSTMs, okay, and simpler than LSTM. While in LSTMs, these are more accurate. If you calculate the if you are running for accuracy, then LSTMs are more accurate and these are more used, more implemented than GRU. If you ask somebody that whether to use GRU or LSTM, so generally people go for more better accuracy for the model. Okay, while GRUs are also quite popular, so you can use any of these networks when you look for a time series kind of data, time series kind of or a sequential kind of data. So these two networks are very very popular. LSTMs are specifically more popular, and we avoid using recurrent neural network because of the vanishing gradient problem. So we don't use them much. Simple RNNs, we don't use them. Now, transformers are also another approach, which is very recent approach. But yes, these are also quite popular. There are many implementations around 2019 and 18 on transformers, although, but that's not in your syllabus, I guess. So we'll skip that part. Okay. Yes, now let's see how do we represent a word. So basically, next topic is application of this LSTM network, which is word embedding, word encoding and embedding. So there is a difference in encoding and embedding. You people are doing one hot encoding since so long, so all of you know what is one hot encoding. So, can any one of you explain what is one hot encoding and why it's required?
Converting continuous to static logical data.
Right. Okay. So we want to represent, basically we want to discretize our data, right? Okay. So so what happens is, suppose we have a sentence. Uh, okay, we have a vocabulary which is having 10,000 words. Okay, 10,000 words, different words. Now, suppose I want to represent a word. This is a sentence. Uh, let's say uh, this. Okay, apple juice is very tasty. Okay, and next sentence is again uh, orange is very tasty. Or there is we are talking about apple in this whole sentence, and there are so many words previous to this sentence, and we are talking about orange juice in this whole sentence. Now we want to predict what is the word over here. Okay, so how, first of all, how do we implement this sentence in RNN? So for this apple, if I want to if I talk about encoding. Okay, encoding. So this is so we have seen encoding. So in encoding, for first word, let's say apple. So this was my, let's say, fifth word in the dictionary. Okay, so this will be represented as a vector. So 0, 0, 0. 0, 4 zeros, then 1 for the fifth word, okay, and so many zeros. This is one hot encoding. So how many zeros? 10,000. So length of vector is 10,000 because I have 10,000 words. So whenever that word is present, it's 1. Whenever that word is absent, it's 0. Okay. Next is, let's say, juice. So this was let's say 1111th word in the dictionary. So rest all would be zeros, and 1111th word would be 1, and rest all would be 0. So this is a one hot encoding example. Okay. So you can see how big these vectors are. If sentences if we I have a 20 word sentence, so how many what is the size of the vectors? 20 words, and each and every word is having 10,000 size vector. So 10,000, 10,000 into 20. So this is itself is a very large set. Okay, which is, this set is for representing only 20 words. So only 20 words is represented in a such huge information, and this information is nothing. Most of this information is zero. Only that part is one where that word is present. Okay, so this is just a waste of memory. So in general scenarios, so to avoid this waste of memory, we use embedding. Okay, so we will see what is embedding. Okay, there is one more disadvantage. So first disadvantage of one hot encoding was, first disadvantage was that size of the vector, size of vector is very large, is large. Disadvantage of encoding. Okay, so first, the size of this vector is very large if we have a huge dictionary. So if dictionary is having 10,000 words, so each and every word is represented in a 10,000 vector. Size of vector is 10,000. Each and every encoding vector is 10,000 size. Okay. Second disadvantage is, suppose I have in my training data, I have learned the sentence apple juice is very very tasty, and I'm talking about apple juice. So whenever this apple is coming in the sentence, so next word is automatically the juice. Okay. Secondly, uh, so whenever orange is coming, so this is in the test data, suppose, and this is in the training data. So test data automatically should find out that apple and oranges are fruits. So this must they must be talking about, and the sentence is almost the same. So they must be talking about juice. Or similarly, so if I'm talking about a fruit, or I'm talking about something to eat, so that must be a food. That must be a food item. If I am talking about I want to eat this dash. So this is an apple, this is a fruit, and this is a orange, this is a fruit. So I will not eat anything that is okay. So there is a similarity in similar kind of word. Okay, so apple and oranges are fruits. So there is similarity in apple and orange. While if you do one hot encoding, there is no similarity in apple, in juice, in orange. While in taste, if I talk about very, this word has no similarity with any of these. Okay, so there should be some similarity index which shows that okay, these two words are similar and these two words are different. So there, this thing is missing. So similarity between words, this thing is missing. Okay, so these are the two disadvantages of encoding. So to avoid this, there was a new concept which said word embedding. Embedding. So embedding says, okay, instead of writing down so many zeros and only one, so that is just a waste of memory. So what we will do is we extract features out of the words. We extract some features and we represent all the words using those features only. Instead of representing the word itself as zeros and ones, we will represent them in the form of features. Okay. So suppose these are the words king, queen, man, woman. These are the words in my dictionary. Okay, orange and apple. If you see, king is not related to orange, but king is related to queen. So sorry. So what do I do to represent these words in one hot encoding? What I would have done this. Okay, but now I don't want to do this. So what I will do is I create a set of features, okay, out of these words, and I will represent all these words into those features. So I will create a set of features. So features are, let's say, gender. So gender is related to king, queen, man, and woman. So this would be -1 somewhere, some value. Okay. This would be, let's say, minus 0.95, and I will give plus 0.95 to this. So it's not related, so it would be 0.0001. This would be 0.002. Okay. So apple and orange do not. Okay. Similarly, second feature was royal. If I'm talking about something royal, it must be associated with king or queen. So I will give zero point 0.9, 0.89, very high value to this. If for this, it can be minus zero point 0.7, this would be minus, then this would be something like that. So I hope you are getting the point. So the idea is 0.01, 0.1. So idea is we are out of these 10,000 words, there were 10,000 words in the dictionary. So instead of representing them as it is, I'm representing it with a set of vectors, and each and every value in the vector is a feature. So feature 1, feature 2, feature 3 was, let's say, food. So I will give 0 value to this, 0.1, 0.001 to this, 0.002, 0.00 somewhat 3, and 0.9 and 0.8. So high value to apple and orange because these are foods. Okay. So this is a word embedding. So in a word embedding, each and every word is represented by a set of features instead of the original feature. Okay. Now if I had this feature set, so these two problems are solved. First is feature set. If I had 10,000 words, feature set is pretty small. Feature set can be, let's say, 300 features. I can extract 300 features out of this 10,000 features, and I can represent each and every word in a 300 dimensional vector. Now dimension of this vector is reduced to 300. Out of this 10,000, it has reduced to 300. Okay. So feature set is reduced. Second thing is matrix shows the similarity. If you see this vector and this vector are similar, okay, this vector, if you see this, there is a negative correlation. This is -1, this is +1, this is 0, and this is approximately 0. So these two values are similar. So this means that king and queen are almost similar. Okay. Orange and apple are similar because this is 0, 0, 0, 0, and this is zero point 0.9 and zero point 0.8. So these two must be foods. Okay. So similarity is also preserved. Now, so in word embedding, what happens is we have to learn this whole matrix is called embedding matrix. So this is the whole matrix. This is called embedding matrix. Embedding matrix E. And dimension of this matrix is number of words multiplied by number of features. So for each and every feature, for each and every word, there is 300 features. So dimension would be feature multiplied by number of words. Okay. So this is the word embedding concept. Now how these values are calculated. So there is additional calculation with respect to weights and bias. You have to learn these embedding metrics. So what happens is we use transfer learning. We have seen how transfer learning works. So we give the embedding matrix some random values and into the model, and we train it, and we learn these values. Each and every value in the embedding matrix is learned using while training. Okay. So if you want to implement suppose you want to you want to predict the next word, identify the next word in the sentence. You have a sentence, he was doing something something, and you want to predict the next word. So you can use the built-in embedding metrics using transfer learning. So what happens in transfer learning? If you visit GitHub or online, you will find so many, sorry, learning. you will find so many embedding metrics, and you can download the weights from there. And this embedding matrix would be having so many, it's a big matrix, let's say 1 lakh words. Okay, so many, it's a big matrix, and using those words, now you have embedding matrix already with respect to each and every word. You can use the same embedding matrix to predict the next word for your sentence. Okay, so transfer learning we use instead of building our own embedding metrics. And secondly, if you have a dictionary size that you can train easily, so you can build your own embedding matrix as well while training the whole neural network. Okay, so generally you use LSTM or a GRU to train the whole network. Okay, any questions, any doubts about this? Okay, I guess no doubts. Then, so this is the example they are showing. So in case of one hot encoding, there is 100, that is a vector. So you have already worked with this already. In text classification, I guess, assignment you have worked that you have encoded your words and you have given those vectors as input features, while in case of word embeddings, you give embedding as your input to each and every cell at every time step. Okay, so this is the difference between embedding and encoding. Sometimes people use these terms interchangeably. You have seen encoder and decoder architecture in the last class. So what do encoder and decoder do is, so encoder architecture is something like this. There is a, it's also a recurrent neural network, a sequential model. Okay, so it generates embedding, basically a representation. So size of input was, if input was 1000, so it would reduce it to somewhat, let's say 2000. Size of this representation. So and then it generates the, decodes this. So this was your input, and it generates the output from this, decodes the output, and this is your final value. So this is the decoder, and this is the encoder. So what is happening is, suppose you have uh, English sentence, English words, word 1, word 2, word 3, word 4, word 5, and it will generate a mixed representation which will represent those words. Okay, after training, it will give you a representation, basically a vector. ठीक है, and vector or a matrix, and this matrix you pass to the next decoder architecture. It will give you the translated into French, translated word 1 into French, word 2 into French, and so on. Okay, so this is used in machine translation. So this same thing is, so this is called encoder, but actually it's a embedding, because in encoder, the you know that in encoding the input output is the same 10,000 words it should give as output. So it's basically not encoding, it's basically embedding, but generally people in case of images call it encoding. Okay, similarly in face encoding. So if you want to compare two faces, that is phase 1 and phase 2, you train a convolution neural network and you generate a representation, feature representation. Okay, and feature representation is a is of smaller size than the original image. So original image um, was very large, suppose. So this feature representation would be somewhat having 2000 neurons. Similarly, you generate the features from this face, let's say 2000 neurons, and you compare these two feature representations over here. So this is called encoding. So if its value is similar, this means these two faces are the same. Otherwise, they are not. So this is example of encoding. So this is also embedding. You can see this is embedding, but people call it encoding sometimes. So this is a very general scenario. Okay, attention network. So we'll discuss this in the next class. So you have to go to LMS now and start doing your quiz. I will start with the quiz. Okay. Okay. Do quiz for module 3. I hope it's visible to you. It's a quick quiz, so